Module 5.3, Psychoacoustics-Sound Localization. Psychoacoustics is the study of how we perceive sound. It is a field that encompasses physics, biology, anatomy, psychology, and many other related disciplines. We'll be taking an overview of several areas of psychoacoustics in the next few modules. Have you ever misplaced your cell phone and asked someone to call it so you could find it? How did you manage to find the phone if you couldn't see it? You listened for it and followed the sound. Did you ever wonder how that works? The reason you can figure out the location and distance of something you can hear but not see is because of binaural hearing. Binaural hearing means hearing with two ears. Because your ears are facing opposite directions and are separated by your head, there are differences between the sound waves that enter each ear. As those sounds go into each ear, your brain recognizes the differences and processes that information as localization cues. Sound localization refers to the ability to locate the direction and distance of a sound source by hearing and not by seeing. It is most likely that we have this ability because of evolution. If a caveman was able to hear a saber-toothed tiger approaching in the dark, and he could tell the tiger was on his left, he would know either which way to run or which way to throw his spear. Without those localization cues, the caveman would likely become a midnight snack for the approaching feline. So, sound localization was a key component for survival. There are two main cues that the brain uses for localization: interaural time differences and interaural amplitude differences. Interaural means between the two ears. Localization by interaural time difference. Imagine a point directly in front of you. If you measured the distance from that point to each of your ears, both distances would be equal. It should be obvious that a sound coming from that point would take the same time to reach each ear. Now, if that point moved to your right, the distance to your left ear would be longer than the distance to your right ear. Again, it should be obvious that a sound coming from that point would reach your right ear a little bit sooner than the left ear. In nature, a shift in position will cause at most a 1 millisecond difference. It turns out that the brain interprets any interaural time difference from 0.1 milliseconds to 35 to 50 milliseconds as a localization cue. So you can artificially create the sense of position by delaying a sound into one ear. So the principle of interaural time difference states, if a sound reaches one ear earlier than the other ear, the sound will be perceived to be coming from the direction of the earlier sound. The precedence effect and the Haas effect are other names for localization with interaural time differences. Localization by interaural amplitude difference. In the same way that a sound coming from a point directly in front of you would reach both ears simultaneously, the volume or amplitude in each ear would be the same. And similarly, as you move that sound to your right, the sound in the right ear will be louder than in the left ear. So, a change in interaural amplitude is interpreted by the brain as a change in location. The changes in amplitude can occur naturally in many ways. The ridges in the pinna cause small reflections and path variations. Those variations cause phase differences which cancel out certain frequencies. Those frequencies will change depending on the angle at which the sound hits the pinna. The brain can recognize these changes and uses them for localization cues. Also, because low frequencies diffract better than high frequencies, low frequencies will bend around the pinna, where high frequencies will not, so sounds coming from the sides and front will have stronger high frequencies than sounds coming from the rear. Likewise, if a sound is far to one side of your head, the sound will have to bend around your nose, face, or head to reach the far ear. Besides just being softer because of the path length, the head causes an acoustic shadow, which again, because of diffraction, will reduce the amplitude of high frequencies reaching the far ear. This is referred to as the shadow effect. When studying localization, researchers will often refer to the head-related transfer function, or HRTF, as a way of describing the differences the head causes in a sound in relation to the location of the sound source. So the following interaural amplitude differences will be interpreted as localization cues by the brain. If a sound is louder in one ear, the sound will appear to come from that direction. If an ear hears more high frequencies, the sound will appear to come from that direction. If an ear hears more low frequencies, the sound will appear to come from the other direction. In general, the brain uses interaural time differences to localize frequencies below 500 to 800 Hz, and interaural amplitude differences to localize sounds of higher frequencies. This is again because of what happens naturally. For a sound all the way on the right side of your head, by the time a sound reaches your left ear, there is about a 1 millisecond delay. For frequencies below 5 to 800 Hz, the phase difference in a sound wave ranges from 0 to 180 degrees, and the brain can sense that difference. As frequencies climb, phase differences approach 0 degrees again, and the time between periods decreases. As the time difference between cycles decreases, it is harder for the brain to detect those differences. The shadow effect results in amplitude differences for high frequencies, not much difference in low frequencies because of diffraction. You've actually used interaural amplitude difference in your car if you've ever used the balance control on your car radio or with your stereo or personal music player. If something sounds like it is far to one side, you move the balance control and the sound appears to be moving in the direction that you move the control. What you are doing is simply changing the volume between two speakers. As the sound gets louder in one speaker, it gets softer in the other, and the brain interprets that change as a shift in position. Alan Blumlein invented stereo in the late 1930s by using two microphones and two speakers. This allowed audio engineers to artificially create a spatial soundscape. The first experiments with localization involved using a pan pot. A pan pot does not refer to kitchen utensils, but is an abbreviation for panoramic potentiometer. A pan pot is generally a knob on an audio console, be it real or virtual. When an audio engineer turns a pan pot, she is adjusting the amplitude between two audio channels in exactly the same way your balance control works. Engineers do this to place the sounds in a stereo sound field. Even though the actual sounds being recorded may be in different locations, using a pan pot can place them wherever an engineer desires. Another way that audio engineers can create the illusion of a spatial sound field is by using stereo miking techniques. One of the first was called XY stereo. A unidirectional microphone picks up sound from one direction and rejects sound from the opposite direction. If you place two unidirectional microphones pointing 90 degrees to each other, one microphone will pick up sounds coming from the left and the other sounds from the right. Then the signal from each mic gets played back on left and right speakers or headphones. There are many other stereo recording techniques, but one is particularly relevant to the information about localization. Binaural recording uses a dummy head with two internal microphones placed at the end of artificial ear canals. The theory here is that the amplitude, time, and frequency differences caused by the head would be recreated in the recording so that when listened back on headphones, the recording should be lifelike. There are two YouTube videos in the module folder that demonstrate this. You will need to listen to them with headphones or earbuds in a quiet location to experience the difference. There will be questions to answer about binaural recording, so be sure to listen to them. As technology has advanced, Audio engineers now have at their hands many tools that allow them to manipulate spatial cues with not only amplitude, but with time, phase, and frequency differences as well. There's even research going on now to create realistic sound fields that do not require headphones. To review, psychoacoustics is the study of how we perceive sound. Binaural hearing means hearing with two ears. Sound localization refers to the ability to locate the direction and distance of a sound by hearing and not by seeing. Localization by interaural time difference. If a sound reaches one ear earlier than the other, the sound will be perceived to be coming from the direction of the earlier sound. Localization by interaural amplitude difference. If a sound is louder in one ear, the sound will appear to come from that direction. If an ear hears more high frequencies, the sound will appear to come from that direction. If an ear hears more low frequencies, the sound will appear to come from the other direction. The shadow effect refers to the fact that the head causes an acoustic shadow for sounds that have to travel around the head to the ear. Localization cues occur naturally, but can also be created artificially. Stereo refers to having two sources of sound to create a spatial sound field.